Good morning, students. I'm Professor Priya Sharma, PC Department, SIRT College, Bhopal. Say Janandam. So, this is our lecture 7 of the lecture series Digital Circuit System, which we are running nowadays. So, the lecture 7 is on the topic flip flops. So, basically, what is a flip flop? A flip flop is a digital electronics. In digital electronics, it is a circuit with two stable states that can be used to store the binary data. Flip-flops and latches are the fundamental building blocks of the digital electronic system. Both are used as a data storage elements. So basically, there are four types of flip-flops: SR, JK, D, and T flip-flops. Coming to the SR flip-flop, the simple flip-flop circuit which has a set and reset. The full forms of SR are set and reset inputs. So you can see over here, a clock input is given to the NAND gate of the SNR. NAND gate and SNR are the other inputs. These inputs are again passed through a latch, SR latch, having the NAND gates, and their outputs are being fed back to the other NAND gate, and we produce two outputs, Q and its inverted output, which is Q bar. This is the truth table of the SR flip-flop. When the clock is not given, irrespective of the values of the S and R, the output will remain in the memory element. When the clock is given 1 for the entire cycle, then depending on the values of the inputs, the output changes accordingly. Like for when S and R are 0, 0, the output will be the memory element and the next state will be the present state. For the inputs 0 and 1, the output will be 0, 1 and the next state will be 0. For the 1, 0 inputs, the output will follow the inputs and the next state will be 1. For the 1, 1 input, this is a problem in the SR flip-flop as this condition cannot be used and is considered as a invalid state. Now coming to the characteristic table. From the truth table, we can draw the characteristic table. Like we take the inputs as Q1, S, and R, and the output is taken as Qn plus 1 for the characteristic table. If you look at the truth table of the SR flip-flop, when the Qn is 0 and S and R are 0, 0, suppose Qn is 0, S and R are 0, 0, and Qn is 0. The output is in the memory element. So, the output is the Qn. Next state is the Qn. So Qn is 0. Again, when S and R are 0, 1, S and R are 0, 1, the next state is again 0. So we have taken this 0. When the S and R are 1, 0, over here you can see as S and R are 1, 0, the output is 1. S and R are 1, 0, the output next state is 1. When the S and R are 1, 1, S and R are 1, 1, the next state is invalid. So we have used don't care over here. Again, when 0, 0, the Qn plus 1 will be the Qn. So here Qn is 1. So this will, I have written 1. For the 0, 1, the output is 0. For the 1, 0, the output is 1. For the 1, 1, the output is in don't care condition. Now from the characteristic table, we can draw the excitation table also of the SR flip-flop. In the SR flip-flop, the inputs are Qn and Qn plus 1 and we take the outputs at S and R. Now excitation table can be made using the characteristic table. So when Qn and Qn plus 1 are 0, 0, if you look here, Qn is 0 over here and Qn plus 1 is 0 over here only. In these two combinations, the S is 0 and R is 0, 0 and 1 both. So S is 0 and R changes from 0 to 1. So I have written don't care. When Qn is 0 and Qn plus 1. When Qn is 0 over these four states and Qn plus 1 is 1. So this is the only intersecting stage. So here S is 1 and R is 0. So I have written S is 1. Okay, there is one more state. Okay. We will consider this also in the don't care condition. Like we have taken 1 over here. So S will remain 1 and R is changing. So S will remain 1 and R changes. So we have used this don't care. When Qn is 1 and Qn plus 1 is 0. When Qn is 1 and Qn plus 1 is 0. So we will consider this case and this case. In these two cases, S changes from 0 to 1 and R remains 1. So S will be don't care and R will be 1. In the 1 1 condition, qn is 1 and qn plus 1 is also 1. This is this condition, and this the condition. S changes and r remains 0. So S changes, that means it is taken as don't care, and r remains 0. So this is how we use the we can make the excitation table using the characteristics table. Using this excitation table and solving through K map, we could drive a characteristic equation for the qn plus 1, which comes out to be S plus R bar Qn. So this is the basic characteristic equation of a SR flip-flop. Coming to the JK flip-flop, it is the improvement in the SR flip-flop. When S and R equal to 1, the condition arises which is invalid for the output. But in JK flip-flop, it has been solved by just putting some connections in the same SR flip-flop. The final output Q bar is connected to the J input, and the final output of the Q is connected to the K input. So the condition of SR equal to R equal to 1 has been resolved using this. So this is the basic truth table of the JK flip-flop, where the 1 1 input of the JK will give the output as Qn bar. Again, this is not a stable state, it is a toggle state. From the truth table, we can draw the characteristic table as I have described earlier for the SR flip-flop. The procedure is same. And from the characteristic table, we can draw the excitation table of the flip-flop. And through excitation table, we can drive the characteristic equation. So for the JK flip-flop, the characteristic equation comes out to be Qn plus 1 is equals to JQn bar plus K bar Qn. Again, for the D flip-flop, D stands for data flip-flop. The output can only be changed at the clock edge, and if the input changes at other times, the output will be unaffected. This is basically the same as the SR flip-flop, only the inputs are connected. Both the inputs are connected using an inverted gate. An inverter is being used and the inputs are connected simultaneously. So these are the truth tables and the characteristic tables of the SR flip-flop. As you can see, the output follows the input in the D flip-flop. If it is 0, output will be 0. If it is 1, output will be 1. So this is the truth table and this is the characteristic table. From the characteristic table, we can drive the excitation table. And from the excitation table, the characteristic equation of the D flip-flop comes out to be that Qn plus 1 is equals to D. For the T flip-flop, it is the full form of T over here is the toggle flip-flop, is basically a single input version of the JK flip-flop. The JK flip-flop is being used and both its inputs are fused together and given to the NAND gates. So this is the T flip-flop. These are the truth tables and the characteristic tables of the T flip-flop. If the input is 0, the output will be the same, and if input is 1, the output will be the inverted input. This is the excitation table of the characteristic. Uh, this is the excitation table of the D flip-flop. And from the excitation table, the characteristic equation can be drawn, which comes out to be Qn plus 1 is equals to TQn bar plus Qn T bar. To solve this master JK flip-flop using a T flip-flop, as you know, as we have seen a problem in the JK flip-flop that using both the inputs as high, there is a toggling in the output state, as we have written don't care over here. So this can be resumed using a master slave JK flip-flop. The output state of a master slave SR flip-flop is undefined upon returning the control input to 0 when S and R, if both the inputs are high. It is necessary to avoid this condition. So the master slave JK flip-flop allows its two information input lines to be simultaneously used. It results in toggling of the output of the flip-flops. This is the basic circuit diagram of the JK flip-flop, in which we have used two JK flip-flops and a clock input is being used for the master. This is the master flip-flop and this is the slave flip-flop. When inverted when the clock is 0, the slave flip-flop will be on, and when the clock is 1, the master flip-flop will be on. Hence, both the inputs for the J equal to K equal to 1, any one of the flip-flop will be on and will get the output. Operation has been described here that when both the clock pulses goes high, the slave flip-flop becomes inactive and the inputs J and K can control the state of the system. When the clock pulses goes back to low, the information is transferred from master flip-flop to the slave flip-flop and the final output of the system is obtained. From the circuit, it is clear that the master flip-flop is positive level as triggered and the slave flip-flop is negative level triggered. Consequently, the master flip-flop responds before the slave flip-flop. Now, let us discuss the operation of the master slave flip-flop for different combinations of the inputs J and K. So, when both the inputs are low, JK flip-flop will remain inactive and hence the output Q remains unchanged. This is the whole state of the master slave JK flip-flop. When J input is low and K input is high, the output Q dash of the master's flip-flop is high and goes to the input K of the slave flip-flop. The clock signal forces the slave flip-flop to reset. Therefore, the slave flip-flop has the same output as the master flip-flop, that is Q dash and high and Q will be low. This is called the reset state of the master slave flip-flop. When J is high and K is low, the output Q of the master's flip-flop is high and goes to the input J of the slave flip-flop. The negative transition of the clock signal sets the slave flip-flop, hence it is called the set state of the master slave flip-flop. When both the inputs J and K are high, for this input combination, the master flip-flop toggles on the positive transition of the clock pulse and the slave flip-flop toggles on the negative transition of the clock pulse. Hence, the problem of the race around condition of the JK flip-flop is being solved using the master slave flip-flop. Coming last to the applications of the flip-flops, it is being used in the counters, frequency dividers, shift registers and in storage registers. That's all for the flip-flops. I hope it is clear now. In case of any query, you can contact me. All the very best. Thank you. Say